Okay, we're going to start Chapter 6 with summarizing possible outcomes and probabilities. We've gone over random variables quite a few times, so I think you're pretty familiar with it, but you can pause this if you need to. And we're going to use letters at the end of the alphabet such as X, Y, and Z to symbolize variables and particular values of a random variable. So a particular value might be something like X equal 3 or X equal -1. Now we're going to restrict the use of capital letters such as capital X to refer to the random variable itself. And then we're going to use a lowercase x to refer to a particular instance. So the example is if we're flipping a coin 3 times and we're interested in the results. So capital X would equal the number of heads in the 3 flips. That is the random variable itself. X equal 2 equals how many heads we actually had at a particular time we get flipped it 3 times. We counted how many heads, and there were 2. So don't switch those two or you'll confuse everyone, including me. So what can happen when we do this? What are the possible values that we get for the random variable? For instance, if we're flipping 3 times for a coin, we might get a head once, we might get a head twice, we might get a head 3 times. But how often does each occur? And we're looking at the long run as always. So if it takes on a particular set of separate values, such as 0, 1, 2, that's the probability distribution, and assigns a probability of x to each possible value of the x. For each x, the probability has to be between 0 and 1, and that's inclusive, so that means it can include 0 and it can include 1. And the sum of all the probabilities for the possible x values, for all the possible x values, equals 1, just like with the die. So here's the example with the die. We are interested in the probability this time that the roll of a die is a 3 or less. What can actually happen when you roll the die? You can get a 1, 1/6 at a time, 2, 1/6 at a time, and so on, up to a 6, 1/6 at a time. So capital X means you can get 1 through 6. If you look at these probabilities and you add them up, each one is 6, and there's 6 of them, so you get a total of 1. And each of the probabilities itself, for like the probability of getting 1 when you roll it, or the probability of getting a 4 when you roll it, is between 0 and 1 inclusive. What's the probability that the best of a series, 7 series, will be decided by at least 6 games? This is quite often done in something like baseball or basketball. And I'm not going to go through all these probabilities during the presentation. We can discuss these in class if you'd like. It's discussed, I believe, in more detail in the textbook itself. So the way you can win best of 7 is by winning 4 games or more. If you do that in 4 games, you've swept. If you did it in 5, you couldn't have won the first 4 and then play the 5th because there was no reason to. So you know the 5th one was a win. But one of the prior 4 you had lost, and so on. And they add up the probabilities for the different ways you can do it. And here they're looking, saying, what's the chance it will take at least 6 or 7 games? So we talk about the mean to describe the center, and the standard deviation to describe the variability most of the time. Once in a while we talk about the median and the Q1 and Q2, things like that. And when we're looking at numerical summaries of populations instead of samples, we're talking about something called parameters. And we're going to use Greek letters, and we've been using X bar because we've been looking at samples, and we've been using S because we've been looking at samples. Now we're looking at the entire distribution. For instance, when I talk about the roll of a single die, I know what it'll get. I know the entire population is going to be 1, 2, 3, 4, 5, or 6. And this little letter here that kind of looks like a tilted 6 perhaps is called sigma. The one that looks like a U somewhat is called mu. So mu is spelled mu, sigma is spelled S-I-G-M-A. To find out the mean probability distribution, you simply take the value that capital X can attain, so little x equals 1 perhaps, that's the probability of that happening. You take the sum of all these. It's called a weighted average, which we did for grades last week in class. So you could estimate how you're doing in class. And that allows you to give more weight to things that are more important. In the case of rolling dice or something like that, what's more important basically means it's going to happen more frequently. It's also called the expected value of capital X. We don't say capital X, we just say expected value of X. So the expected value isn't about what we get in a single observation, but what we expect to average out in a long run of observations. Now, weirdly enough, the probability that you get, and the mean of that probability, doesn't actually have to be one of the possible values for the random variable itself. This is about, this example is about responding to risk. Some people naturally respond in circumstances to something that's more risky, even though it gives them the same return, expected gain, and they tell you how to do this with the sure strategy. And then they go into how to do this with the risk-taking strategy. And that'll come up in a few problems that you have for homework or for a quiz. So to summarize the variability, the standard deviation, denoted by sigma, measures the variability from the mean. We actually haven't given it, so don't worry about that. The larger the sigma value is, the larger the variability is. And it basically is describing how far values of the random variable fall, on average, from the expected value of the distribution. So let's look at the probability distributions of categorical variables. So we've been looking at quantitative, like the roll of a dice, so we get numbers. However, you can actually use this for other things, like particular for categories. So you can say married or not married, 0 and 1. You can say cancer or not cancer, 0 and 1. And in that case, a lot of times it's easier to code the things when you're doing some sort of machine programming to look at this. And the mean is simply the outcome coded as 1. Now we look at continuous random variables instead of discrete ones, or instead of categorical ones. And I think you already have an idea what continuous means, and they just remind you here. Now if we look under the bell curve, we're looking typically at intervals. This is why this is particularly important. So if we have a dog whose breed average has an average weight of 50 pounds, and we want to know what's the probability of a dog having a weight between 45 and 75 pounds, we're looking at an interval from 45 to 75 pounds. And each of these intervals we might look at has a probability between 0 and 1, inclusive. And if we look at all the intervals that are possible, basically some huge interval that contains all the possible values, like all the possible values for a dog's weight, the probability of it being in there has to be equal to 1. Because we said all the dog's weights, probability is 100%, or in non-percent terms, 1. So here you see something shaded underneath a bell curve, and that's the interval we're interested in. To the right of that, you'll see some other probability, and this one tails off to the right. It's skewed to the right. This is commuting time. So you can imagine train can take forever to come sometimes, and maybe there's a breakdown that right-hand side gets longer and longer, how long it takes to commute. But you actually have some practical limit on the other. I mean, you cannot commute between two cities in 2 minutes if they're 1,000 miles apart. So a lot of times you'll get that bunching up on one side or the other due to physical constraints. And that ends our section.